All right, the next section is 2.1, linear and quadratic functions and modeling. What you're going to learn is polynomial functions, linear functions, which I know you guys have learned, average rate of change, which is just slope, you learn that, linear correlation and modeling, something from Algebra 2, same with quadratic functions in their graph, and some applications hopefully, because this is used in business and economics as well as in manufacturing. Okay, so a polynomial function looks like this. Now I know this looks ugly, but keep in mind that it's just, the variables are in the base spot right here. So it's an example of this would be f of x equals 2x squared plus 4x minus 5. Okay, where a sub n would be 2 in this case. So this would be the first coefficient, the leading coefficient. And the next coefficient then is, a sub n minus 1, which in this case would be 4. And then and so on. Last coefficient would be negative 5 in this case. So we call this a sub 0, this would be a sub 1, this would be a sub 2. And then the degree, this would be n is 2 here. So there's 2, and there's 1 for the exponent spot, and there's 0. So you can see how, the n is right here. A sub n this is a second degree polynomial, so this is the a sub 2 for the leading coefficient. That's not super important. I mean, you're not going to need to know this at all, but just so that you can have the skill of reading from the textbook and, reading this language of math, that's a skill in and of itself. Okay, so polynomial functions, first of all, zero function, if you have y equals 0, we know what that line looks like. Y equals 0 is just the x-axis. A constant function, y equals a number, that'd be like y equals 2. That's a horizontal line that goes through that value a. A linear function, then if we give it some slope, ax plus b, we know that it has slope a and y-intercept b. So we know that it looks something like that, depending on the slope and y-intercept. And then a quadratic function, depending on where we shift this thing, we know is a parabola with degree 2. Okay, so let's find a linear equation. I know you've done this problem many times, but let's find an equation that goes through the point negative 1, 2 and the point 2, 3. And that's what this function notation says. First of all, I usually use point slope for this, but it doesn't matter. There are other ways to do it. We need to find the slope. So that'd be y2 minus y1 over x2 minus x1, which is negative 1 over 3. So my slope is negative 1/3. And I'll use the first point, x minus negative 1, which would be x plus 1, and y minus 2. There's my linear function. I could obviously distribute this and add 2 to the other side and put it in this slope-intercept form, but I'll just leave it like that for now. So average rate of change is slope, as you can see here. This is just function notation, so it looks a little differently, but this really is just y2 minus y1 over x2 minus x1. Right, it's saying let x be some point and let the second x be at a different point. That's like x1 and x2, and that's like, this would be like y2 and y1. Alright, so average rate of change is just slope. This is not something you're going to need to know, constant rate of change. But it says a function defined in all real numbers is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on its graph. Okay. So let's characterize then the nature of linear functions. Verbal, it's degree 1. We know that the algebraic model is y equals mx plus b for slope-intercept form. It's got a slant with slope m and y-intercept b. And I guess the analytical model would be a function with constant non-zero rate of change. It's increasing if the slope's positive and decreasing if the slope's negative. And the initial value of the function is the y-intercept. Properties of correlation coefficient. We'll talk more about this as we do these problems. I didn't put one in the homework this time. But our R values in our calculator, I've shown you this and I'll show it to you in the future too. It's what we get when we turn our diagnostic on. And basically what we find is that when the data is grouped closer together towards a line for linear correlation, then our R value is going to be closer to 1. And when it's spread out further, our R value is going to be less. It's not as close to 1, let's say 0.7. And when there's no correlation at all, R value is going to be close to 0. If it's a negative correlation, then we can have R equals -1. And if it's not very strong, then like R equals -0.7. Okay, so what we're looking for mainly when we do these problems is a strong positive linear correlation to see if a linear model would represent the data. Alright, so we'll do this regression analysis for these problems which we've done. We'll enter this into our stat plot. We'll find a regression model that fits. We'll put the graph on the scatter plot, and then we'll look at the fit. And we'll use the regression model then to make predictions about the future. We'll do that later, not in this homework assignment. Okay, so let's transform a parabola then. We've talked about how we know that parabolas look like this. Our standard parent function, y equals x squared. Well, this one, we're going to shift it 2 units. If we subtract from x, then move it 2 units to the right. We're going to add 3's outside, so that's going to move it 3 units up. So now we have a new vertex, which is here. We're also going to multiply this by 2. That's dividing y by a number bigger than 1, so that's going to actually make it more narrow. So I'm going to draw it a little more narrow, and I'm going to move this thing over to up 3. Now this is actually in vertex form, so we can talk about vertex form. Vertex form is right here. It's on your formula sheet. A is going to affect how it opens, skinny or narrow, and also up or down. And then H and K is the vertex. Okay, just like how we determine from shifting the function. We can see that those things are true. So let me actually show you this on the internet. Here's a parabola, just a standard parabola. Right now I have these sliders set in so that A is 1. So right now A is 1, H is 1, and K is 1. So this thing shifted over 1 to the right, up 1, and then it's also just has an A value of 1. So let's take a look at A first. A, you can see as A gets bigger, this thing gets a bit more narrow. And you can see as A gets smaller, this thing gets more wide until A is 0. When A is 0, obviously, this whole term drops out, and you just have y equals 1, which is just a horizontal line. Okay, and then as A goes negative, this thing turns into a parabola that opens downward. And as A gets smaller in this case, or a larger negative value, you can see it gets more narrow. All right? And then H, we know that shifts the function left or right because that's our horizontal shift. And then we know that K shifts the function up or down because that's our vertical shift. All right, there's different ways to take a polynomial like this and put it into vertex form. That's what we're going to focus on. We'll show you 2 different ways and we'll call it good. Those 2 different ways are, the first way is to find the x-coordinate for the vertex, which is really H. H is the x-coordinate for the vertex, right? So to find that, we know that's negative b over 2a. That's on the formula sheet. So that'd be -8, which would be positive 8 over 2 times 2, which is just 2. So the x-coordinate for the vertex is 2. There's H. I can find K pretty easily by plugging it back in. When I plug it back in, I get 2 squared. 4 times 2 is 8, minus 16 plus 11. So that'd be -8 plus 11, which is 3. So my vertex is at 2, 3 for this problem. And I can go ahead and plug that into vertex form. I don't know what A is yet. I'm sorry, I actually do. I have x minus 2 squared plus 3. And my A value is right here. It's 2. That's an easy way to put it into vertex form. You know, find H and K. And then this has to be your A value because if you were to FOIL this out, this 2 would get attached to the x squared, which is right there. So that's always going to be your A value, as we know, because it's ax squared plus bx plus c. So that's the easiest way to put it in the vertex form, is to find this, the vertex and steal the A. But there's another way, and I'm going to check your work for this, so I'm going to make sure you know how to do this way, mainly because I need you to know how to complete the square. It's a good skill, especially for conic sections, which we'll cover later. So let's do it that way. We're going to take this one now and put it into vertex form, this time by completing the square. So what we'll do is we'll move over, actually, yeah, it doesn't matter what order you do this in, but I'll add 8 to both sides first. Okay, So I move the 8 over. Now I'll divide by -4, everything through by -4. Make sure you do every term. Okay, that gives me f of x divided by -4 plus -2 equals x squared plus -3x. Okay, now I'm ready to complete the square. So once you get, your c term over to the other side and you get a to be 1, now what you can do is you can add this b over 2, which is -3 over 2 squared, to both sides. So the key to completing the square is adding b over 2 squared to both sides. Okay? Once you get c over and a to be 1. So I'm going to add this -3 over 2, which is 9/4. So I'm just going to add 9/4 to both sides. Now, it factors into a perfect square trinomial from there. So it's going to be x minus 3 over 2 squared. Basically, you just take this and put it there, and take this and put it there, squared. I mean, every time you complete a square, you purposely added something to make it a perfect square trinomial. So it's always going to factor really easily from there. But I do need to simplify all this, so I need to take -2 and add it with 9/4. So I'm going to get a common denominator and multiply on top divided by 4. So this will be -8 over 4, which gives me 1/4. So it's f of x over -4 plus 1/4. All right, now I'm going to subtract 1/4 from both sides to get rid of this 1/4 right here. And then I'm going to multiply through by -4 so that I can get rid of this from the y value. If I multiply through by -4, this turns into -4, and this would turn to +1. So my final answer for my parabola in vertex form is f of x equals -4 times quantity x minus 3/2 squared plus 1. So that's another way to put it into vertex form, by completing the square in the polynomial. This is something, like I said, I want you to learn how to do. So I will ask you to do this both in the homework and on the test, and later when we get to conic sections, we'll do it again. Okay, so quadratic relationships, it's a polynomial of degree 2 verbally. Algebraically, we have two different forms, standard form and vertex form, both on the formula sheet. And with the graph, it's a parabola. We know the vertex is HK, and axis symmetries, x equals, axis symmetry is x equals h. And then it opens upward if A is positive, opens downward if A is negative, and the initial value is the y-intercept, or what you get when you plug in 0 for x, which is just c. All right. So one application of this is free fall motion. I've given you this equation. I think I used different variables, but basically, if you want to find, that's supposed to be height. You can't see that really. There we go. They use S of t, which stands for height. So this is the height equation. It gives you the vertical height as a relationship with time, where the initial velocity is a constant, the initial height is a constant, and gravity is a constant. Okay, so it's a relationship between height, vertical height, and time. And that's what this says. The height s and vertical velocity v are given by this equation. And the function notation kind of gives it away. It's height in terms of time. All right, they give us the acceleration due to gravity is a constant. We'll use feet per second mainly for this class. Normally we would use meters per second, but we'll use feet in this class. So we will use this quite a bit as some application. I put one in the homework, and you've already done one in the homework actually, and we just went up, hopefully, and did that activity where we found out how fast you could throw a ball. So this is an equation we will use, and it's a great application of quadratics. Hope this helps.